Hello, my name is Scott Bailiff, and I'm going to be giving a brief presentation on controlled N-gas autoignition and expanding thermal efficiency of engines. So first off, what is N-gas autoignition? So N-gas autoignition is the spontaneous combustion of remaining unburned fuel inside the cylinder. This is due to increased temperature and pressure as the cylinder compresses the fuel, as well as the flame propagation out from the spark plug. Essentially, as the remaining fuel is put under these increasing conditions, eventually it will spontaneously combust without properly having the flame propagate throughout the cylinder. This is also more commonly known as engine knock, and is a rare occurrence in gasoline engines, but much more common in natural gas and diesel. Some positive impacts of N-gas autoignition is that it allows increased burn rate and combustion temperatures within the cylinder. This goes into the rest of the presentation, which is increasing thermal efficiency of these engines, because allowing up to 25% of the remaining fuel in the cylinder to spontaneously combust, it can actually cause an increase in thermal efficiency of 4%. On top of this, N-gas autoignition also ensures all fuel is burned within the cylinder, thus reducing the harmful emissions emitted from the tailpipe. In light amplitudes of knock, it can even cause smoother engine performance. What I mean by light amplitudes is that N-gas autoignition creates these pressure differentials during the power stroke of the engine. Light amplitudes have very small pressure differentials from the smooth pressure curve you should be seeing without N-gas autoignition within the engine. However, heavy amplitude creates much larger pressure differentials, which then goes into the negative impacts of N-gas autoignition. So the negative impacts of N-gas autoignition, specifically looking at these heavy amplitudes, can actually cause engine damage within the cylinder or the engine block and the cylinder heads. This is mostly because modern engines nowadays are made mostly of aluminum, which is a much weaker metal than they used to be. So through the increased operating temperatures and prolonged exposure to N-gas autoignition, it has been known to cause fatigue failure throughout the engine. On top of that, it can also disturb spark timing, disrupt valve seating, and even cause the failure of piston rings due to these large pressure variations. But if you look at the base values of thermal efficiency and the capabilities of increasing these efficiencies, you get the gasoline, natural gas, and diesel efficiencies being 25%, 39%, and 44% respectively. The fact that these are not 100% as it would be with the Carnot cycle, which the Carnot cycle is the theoretically 100% efficient engine. This is actually physically impossible due to energy losses due to friction, heat loss, and exhaust gases. And what I mean by thermal efficiency exactly is it is mass fuel burned to percent power output of the engine. However, through the use of computer-controlled variable compression ratios, as well as fuel blending and a couple other minor systems, the amount of knock can actually be held at a specific steady state within the engine. But there's this threshold that has to be met between prime engine efficiency and damaging the engine. So the 25% mentioned earlier is actually proven to cause engine damage in modern engines. But if you allow about 11 to 12% of the current remaining fuel in the engine to auto-ignite, you can actually see an increase of about 2.5%. This is actually quite remarkable in looking at modern engines nowadays. So some applications of increasing thermal efficiency within an engine. You have actually much greater gas mileage increases in all types of engines, gasoline, natural gas, and diesel. On top of this, it was shown earlier, it can reduce the emission output on roadways. However, my apologies. So if you increase the burn rates and temperatures, it actually makes it easier to use varying types of biofuels, especially with natural gas and diesel, which thus could expand the global reserves we have of the petroleum and natural gas that's left. It can also allow the internal combustion industry to compete with the ever-growing electric vehicle industry, especially through the utilization of natural gas. The reason I say that is because natural gas currently burns 4 to 5 times cleaner unaided than diesel, and at this current date is 3 times cheaper per unit volume than diesel. So you could save money through the lessened use of resources while also increasing income and stocks of the industries that take on these increased thermal efficient engines. So I would like to thank you again for listening to this brief presentation on controlled N-gas autoignition and the expansion of thermal efficiency of engines. Thank you. Have a nice day.